section 2.7 is going to be on graphing rational functions that may have different asymptotes other than just horizontal or vertical. They could have slant asymptotes, and we'll see what that means in this presentation. Here are some steps 1 through 7. I took these out of our text, but they work. They're an all-inclusive list for how to graph rational functions. Reminder of what a rational function is here. We have a function written as a fraction of two polynomials, and these things must be polynomials in order to be considered a rational function. So the first thing is we're going to simplify the function f as much as possible if we can. Secondly, we'll find the y-intercepts, and that is, we're just going to plug in 0 for x, and that'll tell us what the y-intercept is. Third, we'll find the zeros of the numerator, the top. These are the x-intercepts. This is the values at which the function will equal 0. Fourth, we'll find the zeros of the denominator. This is going to represent the vertical asymptotes. This is the places where the function cannot exist. Fifth, we're going to find horizontal asymptotes using the rules on page 144. That has to do with the degree of the polynomial in the numerator and the denominator. So I'd encourage you to review that. Sixth, we're going to plot at least one point in between and at least one point beyond each x-intercept and each vertical asymptote. And then we connect the graph with smooth curves once we understand the behavior near the asymptotes. So we'll go through several examples here, or a few examples of how to graph. So here's the first one, graphing 8 over x minus 2. So if we follow through with our procedures, first of all, we notice this cannot be simplified. This one doesn't reduce. So what we will do here, first thing I notice is that the denominator, my pen isn't working right here. Let me see if I can fix that. Okay, there we go. The denominator, if it equals 0, this function won't exist. That'll be our vertical asymptotes. So I'll go over here and I'll set x minus 2 equal to 0, and I get x equals 2. So that means at the line x equals 2, which is right here, we have a vertical asymptote. So that is going to be indicated by a dotted line. Okay, once we get that, we are going to find a variety of other things. We'll find, let's say, our intercepts. If we put in a 0 for x, put in a 0 for x, 0 minus 2 is negative 2, and 8 divided by negative 2 is negative 4. So that is our x-intercept. Now when will this function equal 0? If I take the top and set it equal to 0, well, it's not 0. This will never equal 0. So in other words, this function is not going to cross the x-axis. We actually know from the page 144 that since the top here, the numerator has a degree 0 and the denominator has a degree 1. Well, the top is less than the bottom degree. Whenever that happens, we are going to have an asymptote at the x-axis. So we are going to have a blue dotted line here. Now probably already you can determine what the shape of this graph is going to look like. If it's never going to touch either of these two dotted lines, it's probably going to look something like this and something like this up here. So we're going to plot some points to see. We've got one point here. Now I like to look at this and say, all right, what would it take? What are the nice numbers right here? Well, if I could get 8 divided by 2, which that would be true if x is equal to 4. So at the x value of 1, 2, 3, 4, the denominator becomes a 2. 8 divided by 2 is positive 4. So I know it's going to go through this point right here. Also would be nice is if the denominator was 4. Well, that would occur if x is 6. 6 minus 2 is 4. 8 divided by 4 is 2. So I have the ordered pair 6, 2. And what about if it was 8 divided by 8? That would be 1, which means the x value must be 10. So all the way out here at 10, in the denominator, 10 minus 2 is 8. 8 divided by 8 is 1. And I suppose we could look at the x value of 3. 3 minus 2 is 1. 8 divided by 1 is 8. So at 3, we have 4, 5, 6, 7, 8. So that's enough to see what the top part of the graph looks like. I'll try to draw this here. So this curves down and it continues to get closer, oops, and closer and closer and closer without ever reaching either of these two dotted lines. Now down here, similar thing is going to happen. If I put in the value of x equals negative 6, okay, negative 6 is out here. Negative 6 minus 2 is negative 8. 8 divided by negative 8 is negative 1. So at negative 1, 2, 3, 4, 5, 6, negative 1 right there. If we put in x equals 0, we already got that one. Let's say we put in x equals negative 2. Negative 2 minus 2 is negative 4. And negative 8 divided by negative 4 is negative 2. Oops. You get the point. And we could draw it right now, but I'll do one more point here. Let's see what it would take if x equals 1. 1 minus 2 is negative 1, and 8 divided by that is negative 8. So 1, 2, 3, 4, 5, 6, 7, 8. Right there. I'll lower this down here so we can see it. So this graph over here is going to go through these points. Curve down. It's going to continue to get closer and closer and closer to the dotted line without ever touching it, both here and here. And that's the graph of this function. Here's another one for us to try. I encourage you to pause the video and resume it. I'll go ahead and get started here with this. The denominator cannot equal 0, so that means x equals 0 is a vertical asymptote. So we have this. Oops, that's dotted. Okay, so kind of hard to draw over that. Now the numerator and denominator have the same power. When that happens, the horizontal asymptotes have the location at this number divided by this number, so that's 2. So this one is going to have an asymptote up here at y equals 2. Okay. We can find the intercepts. If I put in an x value of 0, we know that doesn't work. This won't work, so it does not have an x-intercept. The y-intercept is going to occur, I'm sorry, I said that backwards. It has no y-intercept. The x-intercept will occur where the numerator is equal to 0. So 2x plus 4 is equal to 0. That is going to give us x equals negative 2. So at x equals negative 2 right here, I know that this function is going to be touching the x-axis. All right, and so we can continue to plot some points here. If I put in negative 1, for instance, the numerator will become 2. The denominator will become negative 1. That's negative 2. So negative 1, negative 2. If we put in a couple others, let's see, if we put in negative 4, 2 times negative 4, that makes negative 8. Negative 8 plus 4 on the top here. Negative 8 plus 4 is negative 4. And negative 4 divided by negative 4 is positive 1. So at the x value of negative 4, we have positive 1. Right here. So that's enough to see the behavior up here. Okay, that's an asymptote. Keeps on getting closer, never touches it. We'll put in a point up here. Let's try to plug in x equals 1. If I put in 1 for x, I get 6 divided by 1 is 6. So 1, 2, 3, 4, 5, 6 right there. If I put in 2, that's 4 plus 4 is 8 divided by 2 is 4. So that's right there. And one more. We'll put in x equals 4. 8 plus 4 is 12 divided by 4 is 3. So I have the x value 4, the y value of 3. That's enough to get the point across. So we draw our graph using smooth curves. You can use the tables in the calculator too to verify that, for instance, on this function, as x gets very, 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 very big, you're still going to be slightly greater than the value of 2 in the y column. I encourage you to check that out and explore that. It's a good way to see the asymptotes that way. Okay, another one here. This one's a little bit more work. I'm going to pause this, get some of the work done, and show it here in a moment. Okay, what I've done here, I simplified this. This one does simplify. The top factors as x minus 2x plus 2, the bottom as x minus 2x plus 3. So when we look at that, one thing we'll notice is the x minus 2's cancel, and we can write this then as equals x plus 2 over x minus 3. Now for that reason, I should erase this here. I drew the wrong line. The asymptote is going to be located where this cannot exist. Well, x cannot be 3. So we are going to have an asymptote here. Now, some of you are probably saying, hang on a second, it can't be 2 either. Well, that's true, but since it factors out like this, and what I mean by that is the 2's cancel, well, then this is not an asymptote. However, at 2, the graph does not exist, and I'll demonstrate that to you in a moment here. So we have our asymptote that way. The horizontal asymptote, because these are both degree 2, well, then what our book tells us is going to be the case is we're going to have this coefficient over that coefficient, so we are going to have 1 as our horizontal asymptote. Again, you can review page 144 for that. Okay. We plot some points in here. X equals 0. I'll pause this and I'll get those points plotted. Actually, what we'll do for that is we'll use our calculator. I just typed in the equation here. And we can use the table and we'll plot some of these points. We have negative 2, 0. No, that's one of them. So x equals negative 2, y equals 0. We'll get a few more of those. We also have negative 7.5. We might want to plot that one. So negative 1, 2, 3, 4, 5, 6, 7, negative 0.5. Oop, positive 0.5. Sorry about that. And we got negative 2, 0. Let's go down this way. Notice the error at 2. That means the graph does not exist there because the original function has x minus 2 in the denominator, but it's not an asymptote. It doesn't exist at 3 either. We have 4, 6, and let's plot 8, 2. So 4, 6, and 8, 2. 4, 1, 2, 3, 4, 5, 6. Hopefully I counted right. And 8, 2. That's enough. We can graph the curve from that. Asymptote, those never touch the dotted line, and over here, the same thing, except something slightly different over here. Oops, I didn't mean to touch that line. We are going to have at x equals 2, which is right here, there's going to be a hole in the graph. So this line should not exist right inside of there. That's how we demonstrate that this is non-existent at that point.